Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1906, Henri Poincaré, a polymath of unparalleled brilliance, published Science and Hypotheses, a work that continues to resonate with profound implications for our understanding of scientific inquiry and the nature of knowledge itself. To fully appreciate this seminal text, it is essential to situate it within its historical and intellectual context, recognizing the significant developments that shaped Poincaré's thinking and the profound influence it exerted on subsequent generations of scientists and philosophers. The late 19th and early 20th centuries witnessed a period of remarkable upheaval in physics and mathematics. Classical physics, underpinned by Newtonian mechanics and Maxwell's electromagnetism, appeared to provide a complete and consistent description of the physical world. However, as the century drew to a close, several anomalies and paradoxes began to surface. These included the puzzling behavior of the Michelson-Morley experiment, the ultraviolet catastrophe in blackbody radiation, and the unresolved problem of the stability of the atom. Simultaneously, in mathematics, the foundations of the discipline were undergoing intense scrutiny, with debates surrounding the nature of infinity, the consistency of set theory, and the role of axioms in constructing mathematical systems. These intellectual crosscurrents compelled a reconsideration of fundamental assumptions about the nature of scientific knowledge and the methods used to acquire it. Poincaré, a towering figure in this period, possessed a unique vantage point from which to engage these challenges. His contributions spanned a vast range of disciplines, including mathematics, physics, and philosophy. His work on non-Euclidean geometry, celestial mechanics, and the theory of relativity established him as one of the leading scientific minds of his time. His profound understanding of both the successes and the limitations of existing scientific frameworks positioned him to critically evaluate the underlying assumptions and methodologies of scientific inquiry. This scrutiny of scientific assumptions informed the development of science and hypothesis. At its core, science and hypothesis advocates for a novel epistemology, emphasizing the role of convention and hypothesis in the construction of scientific theories. Poincaré argued that scientific principles are not simply empirical generalizations derived from observation, but rather they are, to a degree, free chosen conventions. These conventions be maintained though arbitrary, they are selected based on their consistency and their ability to simplify and unify our understandings. The book's central thesis posits that the laws of physics, especially those concerning space and geometry, are in part conventional, reflecting choices that physicists make to organize the physical. Consider, for example, Poincaré's analysis of Euclidean geometry. He did not dispute the empirical validity of Euclidean geometry to the extent that our everyday experience is concerned. However, he argued that the choice of Euclidean geometry over, say, non-Euclidean geometries is partly a matter of convention. Since experiments can only provide observational evidence to a limited degree, it is in part a choice to keep physics and geometry in alignment. The non-Euclidean geometries, like those of Lobachevsky and Riemann, are equally valid as mathematical systems. However, Euclidean geometry is retained because it simplifies the description of physical phenomena and provides a more readily accessible framework for understanding our everyday experiences. Poincaré extended his analysis to the laws of physics, particularly those concerning the nature of space and time. He anticipated many of the insights that would later become central to Einstein's theory of special relativity. He argued that the concept of simultaneity, for example, is a convention, implying that the synchronization of clocks across different locations is not based purely on objective reality, but on practical choices. The speed of light, he stated, is a convention, but it gives us a unified understanding. Although light is a phenomenon with real properties, the speed of light is a particularly useful convention. Another critical contribution of science and hypothesis is Poincaré's nuanced discussion of the role of hypotheses in scientific progress. He distinguished between three main types of hypotheses. The first type, the natural hypothesis, were those which seemed almost unavoidable and were built into the very framework of the problem. The second type he termed the indifferent hypotheses. These are hypothetical frameworks that appear to impact scientific theory, but whose impact can be shown to be inconsequential. It is the third category, the fruitful hypotheses, which held most interest for scientific progress. These were the hypotheses that were deemed likely to lead to further discoveries. Poincaré's perspective on the importance of good hypotheses provided a bridge between the rigor of pure mathematics and the experimental basis of physical science. The book illustrated how scientists formulate hypotheses, test them against evidence, and revise them in light of new findings. He also highlighted the roles of simplicity, beauty, and elegance in the selection of hypotheses. He argued that scientists often favor theories that are thematically elegant and conceptually simple, not because these qualities guarantee truth, because the theory is easier to understand, test, and the direct applications of Poincaré's ideas were not immediately apparent in the way of new technologies or specific scientific breakthroughs. However, their impact was more profound. Science and hypothesis prompted a re-evaluation of the fundamental tenets of science. It challenged the positivist view, which posited that scientific knowledge is derived purely from empirical observation. It also undermined the notion of absolute certainty in scientific claims. Instead, Poincaré advocated for a more pragmatic and nuanced view of scientific knowledge, emphasizing the role of human choice, convention, and judgment in the scientific process. Poincaré's work gained significant traction during the early 20th century, and it was discussed by leading thinkers and scientists across Europe and the Americas. His perspective on the conventional nature of physical laws resonated with the emerging ideas of relativity and quantum mechanics, which drastically changed the intellectual landscape. Einstein himself, in his development of special relativity, was influenced by Poincaré's work on the nature of space and time. Poincaré's insights concerning the relativity of simultaneity and the significance of the speed of light as a fundamental constant provided a crucial groundwork for Einstein's approach. The influence of Poincaré's work on subsequent developments has been multifaceted and enduring. His emphasis on the role of conventions in scientific theorizing paved the way for the development of logical positivism and the philosophy of science developed by philosophers such as Moritz Schlick and Rudolf Carnap. His ideas regarding the importance of simplicity and elegance in theory selection continue to influence the work of theoretical physicists and mathematicians. The recognition of the role of hypotheses in scientific progress remains central to scientific methodology. Poincaré's ideas faced some criticism, especially from advocates of absolute realism, who argued that his conventionalist approach undermined the objectivity of scientific knowledge. Some philosophers and scientists contended that while conventions may play a role in the development of scientific theories, they should remain subordinate to empirical evidence and the objective reality of the world. Others questioned the extent to which the adoption of standards in scientific field is driven by pragmatic considerations. However, the critiques have not diminished the significance of Poincaré's contributions. They helped to clarify and refine his ideas. His work on geometry was foundational for the study of topology and, indirectly, for the development of modern physics. His insights into the nature of scientific knowledge remain as pertinent today as they were over a century ago. The ongoing debates concerning the interpretation of quantum mechanics and the nature of scientific realism repeatedly engage with the issues he raised. Several individuals and prior works directly influenced Poincaré's ideas. His engagement with Euclidean and non-Euclidean geometries, particularly the work of Bernhard Riemann, contributed to his views on the conventional nature of geometry. He drew upon the work of Ernst Mach, who was critical of the metaphysical assumptions of classical mechanics and advocated for a more empirically grounded approach to science. Mach's views on the role of observation and the importance of avoiding unnecessary metaphysical baggage influenced Poincaré's thinking. Poincaré's work also demonstrates a deep understanding of the development of mathematics, including the development of calculus, study of real number. Poincaré's work has also influenced many subsequent works, including the aforementioned influence on developing the theory of special relativity by Albert Einstein. His work influenced the early development of quantum mechanics. His insights into the structure of space and time provided a framework for interpreting experimental results. His work served as a foundation for the development of the philosophy of science and provided a clear framework for the importance of hypothesis. Furthermore, his work helped cultivate a more nuanced perspective on the scientific process. He shifted scientific practice away from simplistic notions of scientific inquiry toward a more critical and reflective approach to scientific investigation. In conclusion, Science and Hypothesis by Henri Poincaré stands as a landmark achievement in the history of science and philosophy. Its core argument for the conventional nature of scientific principles, its emphasis on the role of hypotheses, and its nuanced understanding of the scientific process all continue to inspire scientists and philosophers alike. The book remains essential reading for anyone seeking to understand the foundations of scientific knowledge, the nature of scientific progress, and the enduring power of human reason. Poincaré's legacy lies not merely in his technical achievements, but also in his profound insights into the human endeavor of seeking to understand the world around us.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.